in this part, we're going to have discussed the assignment. The example we have for the pneumatic conveying system. So these are some of the examples, which are going to be similar in many cases, like the final exam or for example, the assignment. We can see that we have the question number 1. We have considered the following system. We have the minimum pickup or the superficial air velocity at the feed point is going to be equal to 19.2 meters per second. The air gas constant given as the R of 287.1 Newton meter per kilogram Kelvin. So the velocity here is known, and we know the length of the pipe, and we have the diameter of the pipe. So definitely this type is going to be the positive mover because it's going to be before the feeder. The given as the polypellets mass flow rate is going to be equal to 10 tons per hour, and the delta PT is going to be 50 kilopascal. The PFE is going to be almost 0 kilopascal gauge. The atmospheric pressure is given as 101 kilopascal absolute, and the temperature is 20 degrees. From this equation, we need to use the previous equations to find the following. First, we need to find the conveying air mass flow rate, the MF, and the solid loading ratio, the M star. Also, we need to calculate the superficial air velocity at the end of the conveying pipeline, the VFE, and the percentage increase of the VFE with respect of the VFI. So we need to find the velocity at the exit. We need to remind the mean superficial air velocity for the pipeline, the VFM, the Reynolds number, RE, and the air-only pipe volume fraction factor, lambda F, and the air-only pressure and drop, delta PF. Assume that we have the pipe roughness to be 0.055 millimeter, and the air viscosity given as rho F is equal to 1.816 multiplied by 10 up to 1 minus 5 Pascal second. This is the first question. The second question is going to be about the negative pressure pneumatic system. So in that case, for the same pickup we have earlier, same velocity at the entrance, and the pressure drop of 50 kilopascal. For the question number 1, we need to remind the exit velocity, percentage of the increase of the exit velocity with respect to the VFI, the MF value, and the M star. Also, we need to find the same air mass flow rate, where the MF is going to be 0.271 kilogram per second. The pressure drop, the PT is 50 kilopascal as question number 1. We remind the value for the VFI and the VFE, the percentage increase of the VFE with respect to the VFI and the M star. And then we're going to consider, consider that the assume that the VT in kilopascal and A and V above are going to be realistic, and which equivalent operating condition A or B do you think is going to work for our application. So we will start with the first example, and this will be something similar to the question number 2, and it's going to be a negative pressure procedure. So once again, we're going to have this system. It's going to be negative pressure because we have the blower at the end. We need an air dehumidifier at the entrance, so we're not going to have the material to be stuck together, sticking together. And we need to design for the following system, where the internal diameter is going to be 100 millimeter internally, and the length is going to be 100 meter in length total. So what we have for this question is a dilute phase vacuum conveying system, shown in the figure 2. Is transferring 10 tons per hour of grain, according to the following specification. First, we have the horizontal conveying pipeline is galvanized steel. Internal diameter is 100 millimeter. The total length of this pipe is 100 meter, and the internal roughness of the wall of this pipe is 0.1 millimeter. So we know the mu value and we know the diameter. We can do our calculation and get the value for lambda, but after we calculate the Rayleigh number. Now, sorry, I should click here. We know what the dehumidifier pressure loss. So we have pressure loss through the dehumidifier of 15 kilopascal. The receiving film filter pressure loss is going to be 5 kilopascal. So across the filter at the end, we're going to have an extra 5 kilopascal loss. The temperature of the air along the conveying pipeline is going to be constant of 20 degrees. The absolute viscosity of the air at 20 degrees is 1.8 multiplied by 10 up to 4 minus 5 pascals per second. Pascal second. Okay. The atmospheric pressure, air pressure is given as 101 pascal absolute. The atmospheric air temperature is 20 degrees. The acceleration due to the gravity is 9.81 meter per second square. The bitumen tube measurements in between the filter and the blower close to the filter, the average air velocity is going to be found as 45.4 meter per second, and the steady gauge pressure of minus 80 kilopascal gauge. So these are some of the sample hand calculation. First, we said that we have a pressure loss of minus 15 kilogram at the due to the humidifier. And here we're going to have minus 5 between the filter and the outlet. The pressure here is reading minus 75 kilopascal. Now, it's minus because we're always going to have a negative pressure. Now, if this one is reading minus 75 and this one is minus 15, so the pressure difference along the pipe is going to be equal to minus 15 minus 75, and this will give me 60 kilopascal. Now, the first thing we are going to do is we need to check what will be the rho. So you remember that we have the following equation. Now I'm going to put the camera and start to explain this step. Okay. I think that the best thing is stop the presentation and just put the PowerPoint here, and the camera is going to be on the other side. Okay, so let me explain to you, after we found the pressure difference, how did we found the value for the density? Now you remember that we had the gas constant, the ideal gas equation, telling me that the E is equal to R E. Okay, so you know that the V is equal to 1 over the density, and thus the density is going to be equal to 1 over. Okay. Now try again to rearrange this equation to find the value of 1 over V. Is going to be as following. That's the pressure. Okay, and this is the RT. So rearrange the equation, and we're going to have that the pressure divided by the RT is equal to the density. Okay, so that's what we have in this equation. At the top, we have the pressure. Below, we're going to have the gas constant multiplied by the temperature. Temperature was 20 degrees, and that's here is going to be 293.15 Kelvin. The gas constant is 0.2871, and the pressure difference is going to be, we have here 101, which is the atmospheric pressure, minus 80 kilopascal gauge. Okay, so this will be the pressure difference, and thus we're going to have that the density is going to be equal to 0.2495 kilogram per cubic meter. What else? Now I need to calculate the MF. The massive flow rate is equal to the density multiplied by the velocity at the entrance multiplied by the cross-sectional area. So we've been given the diameter of the pipe. We've been given the velocity, and we've been given the density. So I can find the MF value, which is going to be equal to 200 kilograms per second. Now we have the, 0.2 kilograms per second. Now we have the continuity equation. So the continuity equation telling me that the value of the MF is going to be constant at the inlet, at the entrance, and the exit. So what we have here, that the density at the entrance multiplied by the velocity at the entrance multiplied by the cross-sectional area is going to be equal to the density at the inlet multiplied by the velocity of the air at the inlet multiplied by the area at the exit. So now what we need to do is we need to calculate what will be the atmospheric, what will be the density of the material at the inlets, because we need to define as much as we can of the unknowns. So here we have minus 15 kilopascal gauge. So the pressure is going to be 101 kilopascal gauge minus the 15 gauge. And thus we're going to have 86 kilopascal. And at the denominator, the gas constant is remain 0.2871 multiplied by the temperature, which is 293.15. So the density at the inlet was only 1.0218 kilogram per cubic meter. Now we know the density at the inlet. We know the cross-sectional area at the inlet, and we don't know what the velocity at the inlet. So rearrange this equation here. We're going to find the velocity value, 0.2 kilogram per second divided by the area multiplied by the density. And thus we're going to find that the velocity at the entrance was 24.9 meters per second. Now, as we found that, we are going to calculate the velocity at the exit. So what we have as the velocity at the exit, the pressure at the exit was minus 75 kilopascal gauge, and the atmospheric pressure was 101 post. So the P at the exit is 101 minus 75 divided by the R multiplied by the T. So we can find the density at the exit, which is going to be less than the inlet, because now at the inlet, we have more material has been added. At the end is going to be more diluted. So we use the same continuity equation, and then we can find the velocity at the exit of the pipe. Now, these steps actually were straightforward and doesn't have anything to be complicated. Okay, and actually that's the same thing. We're using, yeah. Now we're going to calculate the FM, the VFM, the average velocity. Now, that's very important thing. In the case of the velocities inside the pipe, we're going to have a pneumatic system that running with material inside the pipe. Velocity in and velocity out. The mean velocity is, well, I'm going to check your knowledge about that. It's not. Okay, so the average velocity is not equal to the inlet plus the outlet divided by 2. It's not. But the average density is, like that. So the density mean is going to be equal to the density at the inlet plus the density at the outlet or the exit divided by 2. This one is correct. So if I can find the rho m, the diameter is the same, so the area is going to be the same. We have the continuity equation. I can find that the rho m is going to be equal to the rho, the mf is going to equal to the rho m multiplied by the v mean value multiplied by the area. Now we know the area. We calculated the average density, and this one is constant as 0.2. Then I can find this value. Okay, so just remember when you do the design for the pneumatic system, the velocities are not going to be added as an average, but the densities can be added as an average. So we found the mean velocity in the pipe. For the real number, it's going to be equal to the u value multiplied by the velocity, okay, multiplied by 0.1 divided by the viscosity. We got the value for the real number. The mu over d is going to be equal to the 0.1, which goes to fraction, divided by 100, and this will be 1 in 1,000. Now we are going to go to the Moody gram, and we are going to try to find the value for the lambda average equal to 0.0215. So once again, we have the 0.001, and here we have the 141,000. Let's say it's 142,000. Okay, so I'm going to resketch this one again. So I'm going to duplicate this slide. Take it behind the example here. Okay, so we said that the real number was 141,000, and this will make it somewhere around here. This one 100. I think this 150. Let's consider this 150. And here we have the 0.001. So the intersection is going to be first with this line here, and then we're going to take this one up, and we can find the value for the lambda here. It's something about 0.024. Let me check what I got earlier. 215 for a second. That's 2. Talking about the 001. So this is the curve. And then we're going to go horizontally. Oh, yeah. Sorry. I'm going to go a bit down like that to be horizontal. Yep. So we're looking at 0.021, 0.022. I think 0.022 is going to be more accurate. That's what we got earlier, 0.0215 for the lambda. We put on the equation of the delta PF, and thus we are going to be find the pressure difference for the flow, which is 10.84 kilopascal. Next week, I'm going to have the assignment question. I'm going to explain that to you in more details, and actually you can see that the answer, I can show you that, and not going to be much different from what we have here. I have everything here. Just remember that we always going to have a constant area for the pipe, most of the cases, unless if the pipe is going to have multiple sections. The continuity equation is very important, that the velocity at the inlet multiplied by density at the inlet multiplied by the cross-sectional area at the inlet is going to be equal to the density multiplied by the velocity multiplied by the cross-sectional area at any point along the pipe. The density can be calculated by using the ideal gas equation, the pressure divided by the RT, and we can find the density at the inlet, we can find the density at the outlet, we can find the M star, which is going to be equal to the MS divided by the MF. Also, we do have, for the velocities, the velocity average is not going to be simply found by adding the inlet plus the outlet divided by 2. No, we need to use the continuity equation once again to find the value for the average velocity. What we found here, and row number is going to be equal to the velocity multiplied by the rho multiplied by the L divided by the U, and we can find the row number, use it along the value for the coefficient of friction and the diameter, and with Boole diagram we can find what will be the value for the lambda. So as short as that, actually, this question doesn't require to have too much explanation. It's just something we recall from the fluid dynamics. And as I told you, within this week, this Thursday session is going to be about the assignment question for the assignment number 4. Actually, this week we should discuss the assignment number 3. Anyway. This week I'm going to discuss assignment number 3, which is going to be available for you on Friday after the due date for the assignment number 1. And then the week after, we're going to have a discussion about the pneumatic and the hydraulic system examples. I don't know if you mind to have the quiz during the first week after the semester break. Is that going to cause any problem for you if you're again? Because actually, I think that the lecture is going to be pre-recorded, and plus you're not going to attend a real lecture, but instead of that, you're going to have to prepare for 1 hour any time rather than 1 day. And during this time, you're going to prepare yourself for 90 minutes, run the quiz. I'm going to be with you at the beginning of the quiz to explain the question for you, which mainly is going to be based on the example we're going to discuss next week. And I can be available for you for the whole 90 minutes. If you have any question, then you can start asking me. I think basically that the best time to do that is going to be, if I'm going to say Thursday, I know that most of the students actually are working after 6, and this is not going to be fair. I'm sure that nobody will like to be available online during the Easter day and start to do the quiz. So I don't know. Maybe we can make a vote later and find what will be the best day that suits everyone, not only the majority. When I say everyone, that's mean everyone should be available and do the quiz. It's quiz. So even if I get to bring you during above the time holiday, it should be acceptable. Anyway, I will figure it out. So I'm going to give you a look on the next topic we have for this subject, which is going to be the hydraulic conveying. So I'm going to start the recording for this example, and we're going to start a new recording for the next topic.